Hi everyone. Now I am going to explain common emitter configuration. In the previous lecture, we had observed that what happened and how to connect the common base configuration, and by connecting common base configuration, what is the behavior of the transistor at input side and output side by measuring the input characteristics and output characteristics. Now let us see common emitter configuration. What is common emitter configuration? When a transistor connected, emitter terminal is connected to ground and base terminal is connected to input and the collector terminal is connected to output, then the transistor is said to be in common emitter configuration. So emitter is common terminal for both input and output. In this connection, the input is applied between base and emitter terminal, like it is a emitter terminal connected to ground. Input is applied between base and emitter terminal. The output is measured, output is taken between collector and emitter terminal. This connection is most important and one of the most commonly used connection for an amplifier, common emitter configuration. When we see a transistor in the network, electronic networks, it must be one among the any one configuration. Then only it is possible to measure. Transistor is there in the network means it is must be any of the configuration. So in this common emitter configuration, we can measure input characteristics and output characteristics. Now we'll see connection, how to connect the common emitter configuration. Take the transistor symbol. Emitter terminal, NPN transistor. Emitter terminal is connected to ground and the base terminal is connected to input side and the collector terminal is connected to output side. By providing a battery VBB and a VBB to the input side, input base, and VCC is connected to collector. So in order to measure the input voltage by providing a parallel connection of voltmeter and by connecting in series with the ammeter, and at output side measure the current by connecting a series ammeter in the output collector side and a voltmeter at a output side. Students, here have you observed that the voltmeters and the ammeters? The ammeter which is used at input side is microampere because emitter base terminal is input terminal. The current flow in the base is always measured in microampere. So very less current flow in the base terminal. That's why I am putting microampere current. And at output side we use same milliampere. And voltmeters are 0 to 10 volt range at input side and output side. This is the potentiometer. We can represent it at simply fixed resistor. We can use potentiometer. By changing the potentiometer, we can change the battery. We can change the voltage across collector to emitter and voltage across base to emitter. This circuit arrangement can be set up and see that procedure. We can measure input and output characteristics. Here also we can see that common emitter configuration behavior can be explained by two set of characteristics. One is input characteristics and output characteristics or collector characteristics. Input characteristics. According to definition, input characteristic is the graph between input current. So take the transistor in common emitter. Emitter is terminal common. Input is connected to base. Output is connected to collector. So what is input characteristics? A graph between input current. The current input terminal is I base terminal. It's a graph between input current IB. Input voltage base to emitter voltage. It is a emitter terminal, the base terminal. Voltage between base to emitter is VBE. So plot between input current IB, input voltage VBE by keeping constant of VCE, output voltage VCE. Output characteristics. Output characteristics is a graph between output current. Collector terminal is the output current, output terminal. So current flow in the collector is nothing but IC. It's a graph between IC versus VCE, voltage between output terminal, collector and the respective emitter, by keeping input current IB constant. These are the definitions for input characteristics and output characteristic. Now we will see input characteristic, how to obtain input characteristics, how to achieve input characteristics by following this procedure. So the input characteristic of transistor configuration, this, if you see this circuit arrangement as shown in the figure, first, if you see here, adjust the collector voltage. Collector voltage means voltage between collector and emitter, VCE, to some positive voltage. Let us take 0 volts or 5 volts or 10 volts. Consider 0 volts in this case. Then increasing the base to emitter voltage, nothing but input voltage, in a small suitable steps, and record the corresponding values of base current at each step. By keeping output voltage constant, changing the input voltage and note down the input voltage and input current, and plot the graph between input side, input current and input voltage by keeping output voltage constant. So when we plot IB versus VBE by keeping output voltage constant, and we will get one graph, input characteristic graph. And when we repeat this about 3 steps, for VC is equal to some other value 10 volts or some other value 20 volts, we will get some other graph. These 3 graphs we'll see in the input curve. Let us see here. So by keeping VC 0, we'll get this graph, and VC 10 volts, we'll get this graph, VC 20 volts, this graph. When we observe this input characteristics again, here also again, due to early effect of base width modulation, then the direction of the curves are, the curves move right side when increasing the output voltage from 0 to 10 and then 20. Curves move right side. And then one more important thing is base current decrease by changing the output by collector to emitter biasing voltage. Collector to emitter voltage increasing, IB decreasing, curve move right side. What is the reason this current decreasing? Very simple. 2 junction, emitter base junction. This is emitter base junction, this is collector base junction. Emitter base junction. This is collector base junction. Collector base junction increases, base width decreases. Base width decreases. BCB increases. Junction width collector to base junction increases, then base width decreases. This base width leads to base current flow in the base decreases, so that output voltage increases, base current decreases from this point to this point. That is one thing. Next, why the curve move? This one. Let us take a constant line, 40 microampere. Remember students, here y-axis measured in microampere, x-axis measured in volts. Take a constant line 40 microampere. Let us take VC is equal times setting 0 volts and then measure the 40 microampere at 0.8. So at 0.8, by keeping output voltage constant and measure the input voltage will be 0.1, 0.2, 0.3, 0.5, 0.6, 0.8, you will get the 40 micro. If you increasing the collector to base voltage 10 volts, then base width decreases. When base width decreases, base region is very small. If you the same, for example, the earlier, this is the cross-sectional area of the base, you will get 40 microampere. If base width reduce this one, due to this small region, you will get same 40 microampere at 0.8 volts. Absolutely not. So by increasing the base to emitter voltage for this constant 40 microampere to get is always greater than 0.8 volts because of this small region. So when we are biasing increases at the input side, earlier we will get 0.8 volts, we will get 40 micro. Definitely because of this base region is very thin, that same 40 microampere you will get at same 40 microampere will get for this curve is greater than this one. This same 40 microampere for this one is 0.85 or something else. Same 40 microampere will get for this curve, for this VC is equal to 20, you will get almost 1 volt. It requires 1 volt to get same current because base width is reduced. So that's why this curve moves right side due to base width modulation or early effect. And here also we can take the important point. One is, it is a common emitter. What is the input resistance? By measuring change in voltage to the corresponding change in current. And the second one is, what is the current voltage? It must be, transistor must be on whenever it is reached to current voltage. By seeing this graph, transistor always operated greater than this region. So always operated in this region only, greater than current voltage. Now we will see output characteristics. Here, in this output characteristics, it is a graph between IC versus VCE. In this output characteristics, output current IC, output voltage VCE, by keeping input current constant. So in this common emitter configuration, base is the input current, collector is the output current. By taking the y-axis IC current and IC voltage VCE, output voltage VCE, by keeping input current is constant. How to keep input current constant? Whether it is zero current or greater than zero current? By varying input voltage. How can we take this input current constant? By taking the input battery, varying the input voltage and set at a certain voltage at a input side and then set at certain current flow in the base terminal. Let us see the output characteristic. The output characteristic can be explained with the three regions which are called cutoff region and active region and saturation region. In all configurations, output characteristics can be described. Output characteristic can be explained with these three regions. One is cutoff region. First, we will focus on cutoff region. So, as I said earlier, when two junctions, emitter base junction, collector base junction, when these two are reverse bias, cutoff region, forward and reverse active region, forward and forward saturation region, active region, cutoff region. Okay. So according to procedure, keep input current IB is equal to 0. When keep input voltage IB is equal to 0, here it is 0 means 0 current means voltage also 0. When it is 0, emitter connection is 0, no open terminal. Emitter base junction is open terminal. So when it is an open terminal or 0 volts means reverse bias. Input junction is reverse bias. And now increasing the collector to emitter voltage. Increasing emitter voltage, this is a reference as VC SAT. I will explain what is VC SAT. So when greater than VC SAT, all points represents the reverse bias connection at output side. VIB is equal to 0 represents reverse bias. VCE greater than 0.2, VC SAT reverse bias. So both are reverse bias. It is cutoff mode. So input is open terminal. Only current flow due to collector to emitter reverse bias connection. So reverse bias connection between heavily doped emitter, moderately doped collector. So whenever two regions are some reasonable dopings, definitely a significant current, minority current, reverse saturation current flow between emitter and collector terminal. That can be represented with this dashed line. This dashed line is not fall upon the x-axis, but it will show some significant current because it is collector to emitter is a reverse connection. Reverse bias connection between two layers which are having a doping. One is heavily doped and another one is moderately doped. So a significant current flow. That significant current in measured in milli, that's why we can take the dotted line. So even the cutoff region also we have significant current. Okay. Next reason is active reason. When IB increasing 0 to 10 microampere. How it is possible 10 microampere? When input bias increases, input voltage increases greater than cut-in voltage. So input transistor must be on. So when it is on, it is forward bias. Whenever it is forward bias, it must be on. And by increasing the output voltage greater than VC SAT, it is always reverse bias points. So it is reverse bias. IB 10 microampere is forward bias. So forward bias input side, reverse bias output side. It is always active region. In this active region, what happened? By keeping some 20 microampere, by varying the emitter base to emitter junction voltage and set at 20 microampere. Now increasing the collector to emitter voltage slowly. When increasing the collector emitter voltage slowly, the graph will get this one. A small slope will be observed in the common emitter characteristic. Compare with the common base. Common base exactly 0 slope. But whereas in common emitter having some slope. Okay, that is the difference. When we goes on increasing the IB, emitter base junction 20, 30 micro, 40 micro, 50 micro, that the slope current is increasing. Okay, so slope of the curve increasing. Now this region is called active region. Now we will see saturation region. What is saturation region? Whenever input junction forward bias due to all red color regions, nothing but greater than IB greater than 0. And what is this small region? 0 to 0.2, we see SAT point. For this 0 to 0.2, collector to emitter junction is forward bias. In this region, when we small change in small suitable steps in the VC SAT region, like 0, 0.1, 0.2. A change in 0 to 0.1 or 0.1 to 0.2, a sudden increment in the curve. For example, I am taking 60 microampere at input side and varying 0 to 0.1, immediately that small change in 0 to 0.1, 60 micro, almost 58, 59 microampere current increment in the collector. 6 microampere current, 6 milliampere current. By keeping input 60 microampere, it will reach to 6 milli 6 milli. Sharp region. This sharp region is called saturation. If you kept 50 micro and small change in voltage in saturation region 0 to 0.1 or 0.1 to 0.2, large change in, and which is equal to 5 milliampere. So this region is called, this shaded region is called saturation. In this saturation region, so it is not, we are not operated transistor act as an amplifier. So cutoff region, both junctions are reverse biased, it acts as an off switch. Saturation region, both junctions are forward biased, it will be used as on switch. So whenever transistor acts as a switch, we must switch from saturation to cutoff to saturation. But when we used as an amplifier, we must operate it fixed. We must maintain that point, operating point on the active region only. This entire region, we can operate it entire region. So this is output characteristics of common emitter configuration. Here also we can measure the output current or collector current for this CE configuration. Now we will see what is the output collector current. So IC is equal to total IC majority, IC minority. What is IC majority? IC majority, emitter base junction, collector base junction. Due to forward bias, large current flow. Due to reverse bias, only reverse bias alone, minority current flow. So summing these two currents reach to collector, IC majority and IC minority. So here, how to measure collector current in common emitter? We have a formula, IC is equal to common base configuration formula, alpha IE plus IC B0. But this terms, IC, collector current IE, is not input current in the common emitter. In the common emitter, base is input. So in order to get this entire equation in terms of input and output current, in terms of input current, replace this IC. We have a formula, total, we have a formula, emitter current is equal to sum of base and collector current. So we use this one here, IE current nothing but IB plus IC B0. Then expand this alpha IB plus alpha IC plus IC B0. Then take the IC terms on left side. Here also IC term, here also IC terms. So take the IC terms left side and take the common IC. IC if you take common, 1 minus alpha is equal to alpha IB plus IC B0. And take the only IC term left side and we can pass this 1 minus alpha on right side. Alpha by 1 minus alpha into IB plus 1 by 1 minus alpha into IC B0. So this alpha by 1 minus alpha is called beta. We can represent this one is beta. So that's why IC is equal to beta IB plus 1 by 1 minus alpha from the alpha beta relation I will explain later. 1 by 1 minus alpha represented by 1 plus beta into IC B0. This also can be represented by ICs. This can also be represented by beta IB plus minority current ICE0. What is ICE0? Collector to emitter current when base is open. Minority current. Reverse bias, if we measure the reverse bias alone current. Collector to emitter current measured by base term is open. So then at this time, this no majority current, only ICE0. But we can take the equation from common base configuration. That's why I am representing IC B0. So, but the relation between IC0 is and IC B0 is ICE0 ICE0 is equal to 1 plus beta times of IC B0. What does it mean? ICB naught is nothing but common base configuration reverse saturation current. IC naught is nothing but common emitter minority current or reverse saturation current. So when measure the IC naught is always 1 plus beta times of ICB naught. In particular, when we take the beta ranges, which range from 50 to 200, on average that beta value 100. So IC naught nothing but 1 plus 100 times of 100 times, approximately 100 times of ICB naught. That's why in the graph, common emitter configuration, when the base terminal is open, will measure collector to emitter current that is significant. Why it is called significant means this is called ICE naught, common emitter current when base is open. This current is IC naught is 1 plus beta times of ICB naught. So ICB naught is measured in micro, but when multiplied with 100, it will be some few milliampere. So that's why we are showing in the graph with the dotted lines. This most important concept for this, why we have considered this ICE naught compared with ICB naught, because ICE naught is 100 times the ICB naught, 100 times greater than ICB naught. So this minority current in common emitter configuration represented by ICE naught. This can be this is what collector current. So here we can observe what is the important parameters, outcome parameters from the output characteristics. If you see these characteristics, so what we measure, first important thing is we can measure the output resistance. Output resistance can be calculated for particular graph. Change in voltage, for example this graph, change in voltage 4 to 5, 5 minus 4 volts divided by what is corresponding current, maybe 3 minus 2.8 milli 10 power minus 3. This kind of resistance we can measure. So 5 minus 4, 1 divided by 0.2, 1 divided by 0.2 means some 5 kilo ohms, like that. Average medium resistance, medium output resistance, and medium input resistance we measure the input characteristics. So when we compare with the common base, that is what I am saying, medium. If I take the two curves, this is the curve for same input constant, this is the curve for common base, this is the curve for common emitter. The difference between straight line and some slope. So when we take the resistance for this straight line in the common base having maximum resistance, high output resistance, when compared with the slope, a change in voltage corresponding change in current, some reasonable current change. But here same thing, change in voltage, small change in current. When small change in denominator, large change in resistance. So that's why I'm saying the output resistance of common emitter configuration is having some medium output resistance compared with the common base. Common base having high output resistance. And another one is gain. How to measure the current gain? Current gain in the common emitter is called beta. Beta is equal to output current IC by input current IB. So this beta can be measured from the output characteristics. So what is beta? Change in output current, change in input current by keeping output voltage or constant. So if you take this constant term, output voltage constant line, and what is the corresponding input current? Here cross section point, for example 2030, the corresponding emitter current, collector current is some 3 point something, 2 point something. 20 minus 30. 30 minus 20 in denominator and 3 minus 2 in the numerator. So beta denominator 30 minus 20 nothing but 10 microampere divided by 3 minus 2, for example 1 milliampere. So milli micro cancel. So you will get 1 by 10 into 10 power minus 3 and 10 power minus 2 will get 100. Beta is 100. So here that beta value is 100 times. And also we can say here IC is equal to beta IB. When we are giving microampere or input current, it will which will be multiplied by 100 times, will get amplified signal at the output. That's why we can use this common emitter configuration used as an amplifier. Current gain is very large. So these two parameters, output impedance and output resistance, can be measured from the output characteristics. So common emitter configuration, the main purpose is which will be useful for amplifier at an intermediate stage. For the op amps, for example, at an input stage and the intermediate stage and output stage, we always preferred common emitter configuration at an intermediate stage. In this input characteristics, input must be on, cut-in voltage is 0.7, and input resistance is less or medium, and output resistance medium, and current gain is very large. And by seeing this configuration, we can say that the emitter, when it is emitter terminal is common to ground, we can measure the large current flow at the output side. So this configurations, by seeing the characteristic graph, by seeing the input and output characteristics, probably we can measure somewhat the characteristic parameters of the configurations. We can measure common base, we can measure common emitter, and in next class we can see common collector configurations. By measuring those parameters, by measuring graphs, observing the graph input and output characteristics, we can take these all parameters, input resistance, output resistance, current gain and voltage gains. So these parameters are helpful for designing an amplifier. So while we are going to design any amplifier, we must prefer which configuration is best for a particular situation, and what are the parameters which measured from these configurations. So that's why we focus on that, the outcomes of each configuration. So in the next lecture, we'll see that common collector configuration. So today now I'm done with this common emitter configuration. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.